This is magnetism part 7, and first we will discuss how to calculate the magnetic field of a long ideal straight solenoid with the help of Ampere's circuital law. Now first of all we have to know that what is a solenoid. Now a long coil of wire wrapped in many turns around a cylinder is in such a way that each turn is perpendicular with the axis. Now let this be the cylinder. Usually this is made of iron, and if a long coil is wrapped around this iron in this way, then it will be a solenoid. And what we do, we let current to flow through this coil, then this coil or this solenoid will act as a magnet, and these are the turns, and this is perpendicular with the axis of the solenoid. That is, the axis of this cylinder is the axis of the solenoid, and each turn is perpendicular with the axis. And if the turns are closely situated, then it will behave as a very good magnet. The quality of the solenoid or the intensity of the magnetic property will depend on this turn number. Question is that what is an ideal solenoid? Now if this is the coil which is wrapped around the cylinder, then if the radius of that coil, this is the radius and this is the length, when the length is much more than the radius of the coil, then that solenoid will be called as an ideal solenoid. And in an ideal solenoid, it is assumed that the length is infinite, or it is of infinite length. And also in ideal solenoid, the coil will be very closely spaced. In the picture we can see that this is a solenoid. A current I is flowing in this direction through the coil, and we know that when there is a flow of current through a current carrying conductor, then there will be a magnetic field. A magnetic field will be produced around this coil. So here magnetic field B is produced due to the flow of this current I, and we have to calculate the magnetic field, the value of this magnetic field B with the help of Ampere's circuital law. So here for this Ampere's circuital law we need a closed loop, and here we are assuming A, B, C, D as the closed loop in this solenoid. You can also see that this AB is along the axis of the solenoid. If this is the axis of the solenoid, then the side AB is along the axis of the solenoid. The length CD, the side CD of this rectangular closed path, it is totally out of this solenoid, and this CB side, a portion of this length is inside the solenoid and this portion is outside the solenoid. And here also in the AD, this portion is inside the solenoid and this portion is outside the solenoid. Now here the length AB, we are assuming AB as capital L, and in this Amperean closed loop, that is ABCD, the number of turns, this number of turns is equals to N, and DL is a very small length element in the length AB. This DL, a magnetic field B, is generated in the solenoid. We have to calculate the magnetic field in this area ABCD, or in this Amperean closed loop ABCD. Now what we know that from Ampere's law, that B dot dl equals to mu 0 n I. Now here the Amperian loop is ABCD, and this is the sign of closed loop B dot dl. Now we will break up the side, like first of all B dot dl, that is the magnetic field due to this length AB, plus BC, that is the magnetic field generated in this part BC, that is BC B dot dl. Then CD, the magnetic field generated in this length CD, that is CD B dot dl, and then dA, that is the magnetic field generated in this length, that is dA B dl. Now we know from Ampere's law that B dot dl equals to mu 0 n I. So here also this will be equals to mu 0 n I, as this n is the number of turns in ABCD. So this is equation 1. You can see that this dl and this magnetic field are in the same direction, so the angle between them is 0. So what we get, that this portion, for this portion we get that AB B dot dl, this is the dot product, so we may write it as like this, AB B dot B dl cos theta, and here theta is 0, so cos 0 we know that cos 0 equals to 1, so this will be AB B dl, and as B is a constant term here, so here it will be, the integration will be only on dl, and we know that as I said that AB, the length AB equals to L, so this will be equals to BL, and this is equation 2. Why this B dot dl equals to L, integration of B dot dl is equals to L, because the dl is this small portion and we have to sum up such small length elements dl for this total length or for this side AB. So as I said, as I denoted earlier that AB equals to L, so this integration on dl, when the limit is a to b, it will give capital L. So here we can say that for this part the magnetic field generated, for this part the magnetic field generated is BL. Now for this portion, the magnetic field for this length, now we can see that this part is in the solenoid and this part is outside the solenoid. So again we can also see that the magnetic field will be generated only due to this position, and this B will be along this direction and L is along this direction. So here B and dl, the angle between B and dl is 90 degree, and we know that cos 90 equals to 0. So here the magnetic field due to this portion will be 0, because here it will be B dl cos 0, that is B dl, it will be B to C, B dl cos 90, that is, as it is 0, so the whole thing will turn to 0. So for this portion the magnetic field is 0, and for the same reason as for this dA part, this portion the magnetic field will be produced due to this portion, and here also the magnetic field and the length dl is in 90 degree. So for this part B dl AD, this will be also 0, just because of this reason. For this B dl CD part, for this length, this is, we can see that this is totally outside of this solenoid, so there will be no magnetic field as there is no connection with the solenoid. This length has no connection with the solenoid, so for this part the magnetic field B will be 0. So we get the magnetic field only because of this length, and that is BL, and the other parts are 0. Get the magnetic field for this closed loop only because of this length AB, that is BL, and in other cases as the magnetic field and the angle between the magnetic field and the length dl is 90 degrees. So, for this length and this length the magnetic field is 0, and as this is outside the solenoid, so here the magnetic field will also be 0. So, we get for this BDL ABCD for this loop it is equals to BL, and that is also equals to mu 0 n I. From, we can say this from Ampere's circuital law. So, BL equals to mu 0 n I. So, B equals to mu 0 n I, sorry, capital N I by L. Now, we know that what is N by L? N by L is the number of turns per unit length, that is small n. Capital N is the total number of turns and L is the length. So, this is N by L denotes the number of turns per unit length, and that is denoted by N. So, we can write mu 0 small n I. So, B equals to mu 0 small n I. This is number of turns per unit length. Now, we can see that the value of B depends on this small n, but not on this capital N. So, if we have to increase or to decrease the intensity of the magnetic field, we have to change this small n, that is the number of turns per unit length. That is, if this is the cylinder and this is the coil, if the turn is situated in such a gap, and again if this is the cylinder and this is the, these are the coil wrapped in this manner, here we can see that the gap is that the coils are closely situated. So, here the number of turns per length is greater than this solenoid. So, here the intensity of the magnetic field will be higher than this one. So, the value of this magnetic field depends on, as this mu 0 and I, we are assuming that I is a steady flow of current, I is not changing, and mu 0 is a constant. So, it will, the value of this magnetic field will depends only on the small n, that is the number of turns per unit length.